Thank you, everybody. Hopefully, everybody can hear me. And thank you, Professor Chen. That was probably the best ringing endorsement of GaN I've heard in a long time. So thank you. I appreciate it. You almost set the stage for my talk, which is focusing on how GaN is powering the future of AI. Right? So without much ado, I've been involved in the GaN field for about 4 years now. Started my career with GaN systems, specifically on the GaN side, and then subsequently with Infineon, I run their high voltage product line. So let's jump right into it. So, this is a statistic I think most of you know. Currently, depending on the source, it's about 2% of the total world's electricity is being consumed in data centers. And we expect that to go up to about 7%. Now, the time frame of this 7% is debatable. Some people say by the end of the decade, some people say even sooner, based on the growth. But everybody can sort of agree it is growing at an astronomical pace, right? So there is no doubt about that. But that in of itself brings about a lot of challenges, right? Which, if you looked at your traditional, your present AI data center rack, when I started in data centers back, 10, 15 years ago, I would say the typical power was in the single digit to double digit kilowatts. Today, it's tracking at about triple digit, 250 kilowatt ballpark. And if you looked at an architecture in here, it basically, you're taking your transmission grid, and then you're dropping it down into IT racks. It's typically three-phase, goes down to an AC-DC, you have a battery backup unit, and then you have your 48 volt, which is relatively new, I must add. This is only about a decade old, the 48 volt architecture. But it's really taken hold because of the need for a 250 kilowatt rack. The near future obviously takes it towards a 500 kilowatt per rack sort of power demand. That seems to be the way it is almost tracking. And then by the end of the decade, there's already conversation that it will go up to a megawatt per rack, right? That is what we're seeing from most of our customers. Being an Infineon, that we do pretty much the entire solution stack, meaning everything down to the V-core, all the way back and including all the AC to DC and DC to DC power conversion stages you see. Different groups inside Infineon take care of each of those. So we do have visibility into the way it is moving, shifting very, very quickly to the right. Now, as an engineer, I think everyone would agree the best way to bring about power transformation, this is an ideal world, is to take something that's directly off the grid and drop it directly to V-core, right? That's the gold standard or the platinum standard or whatever standard you want to call it. Now, that's more idealized, right? That's something we want to get to, probably never get there just because of the realities of the situation. You can't block that much voltage. You have all this arcing and every other consideration, including some of the considerations Professor Chan brought up, which is delivery of power at those currents at these types of voltages. But you can see that it is evolving. The architecture is going to move towards an 800 volt bus, right? That is kind of the clear direction. And my talk will focus primarily on unpacking this architecture to a great extent, focusing on what are the different elements that constitute this architecture and how GaN best addresses those elements. Okay. So as I said, this is your typical data center rack. If you look at, it's pretty much the physical representation of a data center rack. So if you looked at the top, as the name says, top of rack switches, power supplies, you have your compute, switch trays, another compute, power supply, and then all the way down is your battery backup units, right? And of course, as you unpack these compute and switch trays, you will see that there are, further down in your second stage power conversions, all your CPU boards, your GPU boards, your smart NIC infrastructure, as well as your first stage intermediate bus converters, right? So all of these also are included inside this, the compute tray rack. But more or less, what we'll be focusing on is these four elements, right? The PSU, the architecture changes that we're observing on the PSU side, the battery backup, as well as the IBC, right? So these three elements is what we'll be focusing on primarily. So let's start with the PSU. I think it's been around as long as we can remember. Every compute node, whether that's on your desktop or your laptop or whatever else, has to have some kind of power supply. It varies, of course. But it's also in the data center side. You have your typical PSU rack. Now, currently, in the 250 kilowatt ballpark architecture, these are sort of your two PSUs. There's one on the top, and this is one on the bottom. Now, I will apologize. This is a prototypical rack. It is not universally representative of everything that's out there, right? So there could be other embodiments, other versions of this. So that's always possible and does happen, right? If we dive a little bit deeper into this, you will notice something very interesting, right? So we are seeing an evolution from a wattage standpoint, and these are just some of the Infineon reference designs. You'll see that the evolution is calling for an increase in power delivery, right? So you are walking up from about 3 kilowatts all the way up to about 12 kilowatts. And in the future, they will also be available in a three-phase configuration, something that's well beyond 12 kilowatts. It is under development. Once it comes out, we'll have more visibility. And Infineon's sort of making these individual reference boards, if you will, and making them available to a lot of our customers for two reasons. One is to demonstrate how much power you can pack into as small a space as you can. Second is also gives our customers a way to get started on a design, because a lot of these require a fair bit of engineering in order to get it off the ground, particularly when you're mixing technologies like silicon, silicon carbide, and GaN. And in some ways, coming from Infineon, having all three technologies in-house, we sort of pick the best technology for the given socket, so that we can showcase the best possible way to move forward in a given application, such as a power supply. You'll also notice something very curious here, which is two things. One is you'll notice that the efficiency about remains the same, but you will also notice that your watt per inch, your density, your power density goes up quite dramatically, right? As is indicated by the amount of power that's being delivered. And the reason for that is the challenges from a few years ago till now is primarily morphed into a power delivery problem, right? The efficiencies have hit pretty much where they can hit in terms of a given form factor. Sure, you can squeeze more out of it. You can change form factors. You can change your figure of merit evolution of your individual power device, magnetics, like Professor Chan talked about. So you can evolve that to some extent. But the bigger challenge, the more immediate challenge, is that of actually moving up in terms of power delivery and squeezing as much power delivery into a rack. If you think about it, you're trying to deliver a kilowatt through a rack. So it's trying to squeeze as much as you can. And the reason for that is also very simple. Your GPUs are just getting hungrier. Your compute nodes are just getting hungrier, power hungry. And in the same real estate, you're required to deliver more power. Okay. So these are just some architectures. I used to be an engineer. I don't make to claim to be an engineer anymore, but I will still make a very weak attempt at going at it. So I do apologize if I stumble, but I have, I think, enough engineers in the room who can correct me if I do stumble. So this is a two-level totem pole architecture, a three-level totem pole PFC, and it sort of shows you where you can really make a difference, right? So everything that's in the orange is obviously silicon carbide. Everything is in I guess that's magenta or maroon. I can't quite tell, or purple. That's GaN, and then everything that's green is silicon. So where would you use silicon? You would use it in places where you don't need speed. You would use it in the slow leg. Where would you use gallium nitride? You would use it in a place that actually requires you to be as fast as possible, right? So you can switch as fast as possible. You can avoid the circulating loss, like in the case of this, the synchronous rectifier application. Also in the three-phase LLC, where you don't really have a switching problem. All the losses are concentrated either in your conduction losses or they are concentrated in your gate drive losses, right? So that's some place as well you can use your gallium nitride switches. Right? So these are some ways in a ways to capture this 8 to 12 kilowatt, and it's interesting to see how each technology sort of plays its role. Now today we're here to talk about wide bandgap, and me specifically to talk about gallium nitride. But it would be an unfair characterization to say that silicon has completely lost its space. It definitely has some legs to it. Let's go a little bit further, right? These are more focused on your enterprise data center solutions. these are less space constrained, right? So obviously your power delivery, these are not your AI racks. They're more concerned about your efficiency and to be able to deliver power, but it's not space constrained, and it's not power delivery restricted. So you will see that it sort of tops out at about 3.6 kilowatts. And the biggest difference here is you'll notice the density of these designs is almost much easier to meet, right, compared to the AI sort of applications. Let's now get into the battery backup unit, right? So it's probably, it's probably one of the most underappreciated because it's almost assumed to do its job, right? But over the years, I think what has happened is the battery backup unit has also, a lot of demands have been placed on a battery backup unit. And the biggest challenge with those demands is as your rack goes up in power, you need to be able to store, and the storage element of the battery backup unit takes up the predominant amount of space that is available on the battery backup unit. Right? Excuse me. Bless you. So if you looked in here, the biggest difference is if you were to look at it from a battery backup unit standpoint, it's sitting somewhere here, right? You have your BMS, your protection, but it sort of sits off of a bus, right, in today's architecture. And then everything down the road is just basically a power delivery into your GPU. So it's kind of sitting off to the side, but it is getting more and more critical as, it may not be central to the power flow side of things, but it does become central in terms of how much room it occupies on your rack. Right? So if you look at, as I said earlier, right, if this is kind of a graphical representation of what a BBU will look like, you have a tremendous amount of storage allocated to the battery pack itself, right? If you actually looked at the DC-DC converter or the BMS, those are quite small compared to the actual storage element, right? And as your power density is going up and your BBU power module goes up, obviously battery chemistry is the limiting factor, which means what? It requires your power electronics to subsequently shrink so that you can accommodate for larger storage on your BBUs. And what you can see is, that pretty much tracks, right? You can see the power density goes up quite intense, right? As you are seeing more power being delivered through a BBU module. Some of the solutions Infineon's made is, the focus has been without doubt on the higher power density for Infineon solutions. Because again, as AI and machine learning trends require more power to be delivered, more battery backup is necessary in case of an event, and therefore you need to have higher density because your racks are going up in power. You do see some efficiency increase, obviously. That's also very important because you're kind of coming in and out of the battery pack. And compared to your traditional buck boost, we are optimizing to about 70%, right? So some of the more basic, if you were to sort of do the rack and stack, thermal management is critical. You want to keep it under a certain temperature. You want to keep the size, the cost saving. That's very a par for the course. Okay. This is where I think I might get into a little bit of trouble, which is the intermediate bus converters. There's a lot of debate on intermediate bus converters today in pretty much all of power electronics, right? And here's why, right? So Infineon, we did a study on the intermediate bus converters, right? So 50% of the failures we've found from our reported failures are due to the 48-volt power conversion, right? That is reported to us out of our customer base, right? Now, obviously, this is an estimate. It does cost a hell lot of money if it does go down, a particular rack goes down. But we also did a root cause analysis. And one of the things we did find is while there are unknown root causes, about 13%, the vast majority are actually related to component quality, even as it represents on the 48-volt rack. Now, why would a vendor of a semiconductor stand here today and say, this is a concern? Because this is something we all have to work on. Infineon is dedicated to work on the quality and the system innovation. But given the fact that it's about 35% failure, this is our single-minded focus to actually improve the quality that is being delivered onto these intermediate bus converters. So again, this is again a representation of what could be potential IBCs, and I think Professor Chan went to this in a great amount of detail, including all the losses, and I will stay away from that. But basically, the idea is, you start off with the 800-volt bus, and that's a requirement, as I said earlier, purely because you need to deliver so much power into your 1 megawatt rack, right? You drop it down either to a 50 or a 12-volt bus, ideally 50, because you don't want to bring it down to 12. Your current goes up astronomically, 4 times more than what it will be in 50. And then you have to bring it down to another IBC or medium-volt IBC. And somebody here had asked the question, does it make sense to go from 48 to 0.8? And I think maybe not today, but at some point we may need to even think about that as a potential solution. But as of today, the intermediate bus converters are going down to 6 volts or 12 volts. But the interesting thing that GaN enables is a control topology that has been well understood and yet less utilized for something that takes a 50 volt down to 12 volt, which is a straight interleaved buck, which is quite shocking. And you'll see in the next few slides why I say that, right? So this is your 800 volt to 50 volt converter. This uses 650 volt GaN. It splits the bus into 2 halves, 400 and 400. So it's kind of like a stacking series on this side and then a parallel connection on the secondary side. This is the actual embodiment of it. I won't go into a whole lot of details. Those of you who have questions, come find me later and we can go down the rabbit hole there, right? But basically, the key takeaway is that your power losses in this, as well as the density required to deliver about 6 kilowatt. There's 2 stacked boards of 3 kilowatts per board. So you have to deliver 6 kilowatts, so 3 kilowatts out of this form factor and another identical board of 3 kilowatts, right? So that's pretty small to deliver 3 kilowatts out of, right? 30 by 60. And then this is the more interesting finding that we found, which is your intermediate bus converter, right? If you went back to basic power electronics, our biggest thing was the easiest topology is a buck converter, right? Of all the topologies out there, well understood, control is easy, transients are great, line rejection, load rejection is great. The biggest problem is you drop 48 to 12, and if you did it with silicon, you would take a tremendous amount of power loss. That's why you came up with all these different topologies. A lot of people came up with, including Infineon, came up with topologies such as your switch cap topologies, the hybrid switch capacitor. But we've also noticed that you can make this happen with an intermediate buck, right? What are the shortcomings of your switch cap? The control is more complicated. You typically have an unregulated bus on the secondary side. Your transient response, particularly your load and your line transient, are not very good, particularly with the GPU, which is pulling down a whole lot of power. And most people, when they measure the HSCC, they're measuring at a fixed load, which means you are at the optimal Q point. And when that Q point shifts, as your load shifts, you're probably going to fall out of your optimal efficiency point, and you're going to take a lot of losses, right? Which are usually not captured because your GPU is moving up and down so fast. All of that is sort of avoided with your interleaved buck. You don't need to worry about, because it's already taking all the switching losses. Even if your load moved up and down, your line moved up and down, you're already taking all the switching losses. And so it's almost agnostic towards your switching loss. And so it's truly, if you can match it at static load, which is what we're trying to do here, can we do better with the dynamic? And we think so, for sure. Right? So since I only have about 5 minutes, I want to make sure we have enough time for questions, right? So summary, right? We are, of course, addressing the growing power demand. I think I hopefully demonstrated to everybody here that we are moving from 3 kilowatts to 12 kilowatts and beyond, right? That is very, very important. Hopefully, we've also addressed some of the BBU designs and sort of, I wouldn't say addressed, I would say just touched upon the BBU designs not to ignore that socket, right? It's sort of a call to action, if you will, right? Not to ignore the BBU socket, particularly because the need for storage, energy storage is going up. And then, of course, hopefully we've been able to touch a little bit on the IBC topologies, right, the intermediate bus converters. So, yep. If you need more information, scan the QR code. I'm happy to take any questions.
All right, so we still have a couple of questions to be raised. Open the floor. Any question on this? Oh, sure.
Thank you very much for the great sharing about the gallium nitride for the data center application. I just wonder, beyond the data center, I think everyone is talking about the robots. Can you comment that, how your perspective by using the gallium nitride in the human robot?
Excellent question, right? So humanoid robots, I think the medium voltage GaN and the low voltage GaN plays the bigger role because it's mostly motor control, right, that ends up being the major application in any kind of humanoid robots. But typically the power consumption is lower in terms of what a humanoid robot will demand for a given socket. So it is still GaN, but the bigger challenge there is fitting it into that, that mechanical joint, keeping it light enough and keeping the entire solution small enough so it would actually fit into the humanoid robot, right? It's not really the sheer amount of power delivery that you need to do, unlike in the data center side. Right?
Okay.
So, yeah.
Thank you. Just one more short question. Does Infineon already start to deliver the samples for the robot manufacturing company?
I believe so. I don't run that business, but I believe so, yes.
Thank you. Thank you very much.
Yeah.
Okay, we still can take one or two questions.
Thank you for the excellent talk. You mentioned 37% component failure as a result of some downtime. Would you be able to comment on the nature of those defects? So, like, is thermal induced or pre-existing defects in capacitors and so on?
It varies, right? But it's not really. It's what I call the Swiss cheese model, right? It's the application demands versus also marginal design versus also moving your components in, lack of, let's say, screening or, quality defects. So when all of those line up, the holes in your Swiss cheese line up and then you experience failure. Because if you did have a systemic failure, you would see a much larger failure rate and earlier in your development. But usually, when you go to production, it's usually the Swiss cheese model, right? It's several factors, marginal design interacting with your component. But it's definitely a call to action for the industry at large, right?
More question.
Yes, I know that Infineon has the technology transfer from the Panasonic a couple of years ago. Now, more recently, you acquired the GaN systems.
Yes.
And these two games are different in the gate designs. You have any comments on these two products?
Sure. As somebody who came from GaN systems, I'm familiar, and now being part of Infineon, I'm very familiar with what they do as well. Sure. The Infineon, what was licensed was a gate injection transistor, right? Which is, sort of, if you can think of it, is sort of a BJT or operates BJT beyond a certain point. Whereas the Schottky gate is what your traditional GaN transistor is built off, which was originally a TSMC process, which we in GaN systems sort of adopted and modified a little bit, right? What does that offer? Given the TSMC's, I think this is public news, they've sort of decided to exit the market, so that sort of changed the dynamic. But the original thought during the acquisition was we could support two technologies independently and bring value to the customer through both the technologies. Now that TSMC is sort of, walking away from their Schottky gate, it sort of compels the industry to sort of focus on their in-house technologies. Infineon obviously will be focusing more on our GIT. There's other players who have, Schottky gate, others still who have D mode, which are slightly different than the E mode, ohmic gate. And each one will sort of leverage their own in-house technologies. I think that's what you'll see a proliferation of, right?